Now that we know some basic information about organohalides, let's take a look at the preparation of these compounds. In this video, we'll be looking at how they can be made from alkanes. So alkanes can be converted to alkyl halides by reaction with a halogen in the presence of light and heat. We use H nu because keep in mind energy equals Planck's constant times frequency, or we use delta, capital delta, means heat. So we need light and heat along with a halogen, molecular halogen, to react with an alkane, which can give us an overall substitution reaction. So one hydrogen is replaced by, in this case, a chlorine. This reaction proceeds through a radical mechanism, and so overall this is referred to as radical halogenation. Although the overall transformation in this reaction is a substitution, we need to describe the mechanism in more detail, and so we will be looking at the radical mechanism. But first of all, let's think about some of these terms. So first of all, a radical or a free radical is any species that has an unpaired electron. Any species that has an unpaired electron. Radicals are neutral, but they are electron deficient. They don't have their full octet, and so they are quite reactive. Whenever we consider a radical reaction, we are talking about the movement of single electrons. Now, multiple electrons may move within the reaction, but the electrons are not moving as a pair. Instead, we might have one electron moving in one direction and one moving in the other direction. So with radical reactions, we can think about homolytic bond breaking or symmetric bond breaking. So maybe we have A covalently bonded to B. A homolytic or symmetric bond breaking means instead of both electrons going to one atom, one electron goes to each atom. So one electron goes here and one electron goes here, giving us A and B. So here, our arrow starts at the original location of the electron. So out of these two electrons, one of them moves onto atom A, and the other one moves onto atom B. So the arrow starts at the original location of the electron, and it points to the atom where the electron ends up. In addition, we can have symmetric bond forming. So if we have some radical Y and a radical Z, these electrons can come together. So one electron comes here, one electron comes here. Now we start the arrow at the original location of the electron, and we point to the place where the bond is going to be. So this gives us Y covalently bonded to Z, where this pair of bonding electrons came from one electron on the Y, one electron on the Z. So because radicals have unpaired electrons and they are electron deficient, that makes them reactive. They're reactive because they don't have an octet, and so radicals want to achieve an octet. Now they can do that by abstracting an atom with its bonding electron. So if we have, for example, a radical, and this reacts with some molecule AB, well, this radical can grab A with one of its electrons that used to be shared between A and B, and then that forces the other electron to move on to B. So we get a new bond between our original radical and A, and we generate a new radical, B. Radicals can also achieve an octet by abstracting an electron from a pi bond. That's not relevant for the reaction that we're looking at right now, so I'm going to hold off on that. But there is one other approach, and that is to combine with another radical. That's what it looks like up here. So if we have a radical and it bumps into another radical, then these can combine together. That is a fishhook arrow. These can combine together, giving a new compound with a covalent bond between what used to be the two radicals. Now, this is a possible way for radicals to achieve an octet, but what we're going to see is that we typically form radicals in such small quantities that it's really unlikely for two radicals to bump into each other. They're much more likely to bump into a molecule rather than to bump into another radical. All right, let's keep learning more about free radicals. So once again, it is a species with an unpaired electron. They are neutral, but they are electron deficient, and so that makes them very reactive. So for example, we might have a bromine radical. So it has its lone pairs, but what we want to focus on is this unpaired electron. We might have a chlorine radical. We could have alkyl radicals, such as a methyl radical. We could have an ethyl radical. We could have something like this, where this is a radical, or we could have something like this, where this is a radical. Now, when we are talking about radicals on carbons, we want to be able to classify them based on the carbon that has the unpaired electron. So this is just a methyl group, so we would call this a methyl radical. Here, the radical is on a carbon that's connected to one other carbon, so this is a primary radical. Here, the radical's on a carbon that's connected to two carbons, so this is a secondary radical. And here, the radical is on a carbon that is connected to three carbons, so this is a tertiary radical. So we can have a methyl radical or primary, secondary, or tertiary. In terms of structure of radicals, experimentally, they've been shown to be trigonal planar. Therefore, the radical carbon must be sp2 hybridized. So if this is our carbon, then it's sp2 hybridized. So here's an sp2 orbital, here's an sp2 orbital coming forward, here's an sp2 orbital going back behind, and then there is a p orbital which has an unpaired electron. In terms of stability, it's been shown that tertiary radicals are more stable than secondary radicals, are more stable than primary radicals, are more stable than methyl radicals. Well, how is this information determined? Well, experimentally, scientists can measure the bond dissociation energies. So for example, if we were to start out with propane, and okay, here is this energy. If we form a radical, these are going to be higher in energy, and we have this, which is a secondary radical, and this was shown to have a bond dissociation energy of 413 kilojoules per mole. And then if we have this one, this is a primary radical. This has a bond dissociation energy of 423. So because this can form either a primary or a secondary radical, by measuring the bond dissociation energies, we can see the difference between forming a secondary radical and forming a primary radical. And so primary radicals are higher in energy, secondary radicals are more stable. As another example, if we start out with 2-methylpropane, now what are the radicals that we can form here? We can form a radical here that is a tertiary, or we can form a radical here that is primary. So by looking at the bond dissociation energies, here with an energy difference of 400, this is the formation of the tertiary radical, and then with a difference of 422, This is the formation of the primary radical. So this information was determined experimentally about the relative stability. If we look at a general halogenation reaction, we can take an alkane and react it with molecular halogen in the presence of light and heat to give an alkyl halide with HX as a byproduct. For general halogenation reactions, relative reactivity with respect to the halogens, we're looking at fluorine is more reactive than chlorine, is more reactive than bromine, is more reactive than iodine. Now, fluorine is actually so reactive that this can be explosive. Iodine has other issues, so this is not typically carried out this way, which means all we have to worry about is chlorine and bromine. So let's take a look at a few examples. So if we have methane and we react it with chlorine in the presence of light and heat, a hydrogen will be replaced by a chlorine, and so we will make some chloromethane, along with HCl as a byproduct. However, this molecule can react further, and another hydrogen can be replaced by a chlorine, leading to dichloromethane plus HCl as a byproduct. And then this can react further, leading to chloroform with more HCl as a byproduct. And this can react further to give carbon tetrachloride. So you can go ahead and use lots of chlorine if your goal is to convert methane all the way to carbon tetrachloride. If your goal is to do monohalogenation, so you only want to carry out this reaction once to replace only one hydrogen with a halogen, then typically what you would do is use a large excess of your alkane. So at the end of the reaction, you're going to have leftover methane and chloromethane as your product, and you're not going to get very much of these other species. And then you just have to be able to separate your starting material from your product. If we have something like ethane and we carry out a monochlorination, then we are going to make chloroethane. If this reacts further to give dichlorination, that could either occur at the same carbon or it could occur at a different carbon. And so you're going to get a mixture of products. If you have a molecule such as propane and you carry out a halogenation, even if you control the conditions so that you get monohalogenation, you can still get a mixture of this product and this product. So careful control of reaction conditions is required to obtain a single product, and sometimes even careful control is not sufficient. So let's look at the details of the radical halogenation, and we want to think about the stepwise mechanism. So here we have the overall reaction, and here we are looking at the individual steps. So when we have chlorine, we have to have light and heat because the light and the heat lead to the homolytic bond cleavage, so that we have a molecule of chlorine, one electron moves onto this chlorine, one electron moves onto this chlorine. So what we get is two chlorine radicals. This is called an initiation step because we are going from 0 radicals to 2 radicals. Next, one of these chlorine radicals can bump into a molecule of methane. And when that happens, the chlorine can abstract a hydrogen. So the chlorine will offer up its one electron, and the hydrogen brings one electron to form a new bond between the hydrogen and the chlorine, and then this other electron moves onto the carbon. So now this gives us, we have our CH3, and this carbon is now a radical, and we have made HCl. This step is a propagation step, because we start out with one radical and we end up with one radical. Next, this methyl radical can bump into another molecule of chlorine. So this can combine with one of these electrons, and then this electron moves on to the chlorine. So this radical is abstracting the chlorine with an electron. And so that gives us chloromethane and another chlorine radical. So this one is another propagation step. Let's say this is a really, really small quantity compared to what we would normally use, but let's make the math a little bit easier. Let's say we started out with 1,000 molecules of chlorine. Now, the initiation step is not very efficient, so maybe only 10 molecules react to form 20 chlorine radicals. That leaves us with 990 molecules of chlorine. So, when one of these chlorine radicals bumps into a molecule of methane, we get the methane radical. Is the methane radical likely to bump into one of these 20 chlorine radicals, or is it more likely to bump into one of these 990 molecules of chlorine? It's much more likely to bump into a molecule of chlorine rather than a chlorine radical. So what we're talking about here then is a chain reaction. Once initiation happens, the propagation steps are going to happen many times, so that it doesn't really matter that this first step is inefficient. Once this starts going, these molecules are going to keep bumping into each other. A methyl radical might bump into another molecule of methane and abstract a hydrogen, and you just get a different methyl radical. But it's also likely to bump into a molecule of chlorine, and then we get something different. A chlorine radical could bump into a chlorine molecule, just giving different chlorine radicals, but it could bump into a molecule of methane, leading to something different. So it's very important to keep in mind that we are talking about a chain reaction, that it is very likely for a radical to bump into a molecule, or this radical to bump into this molecule. It is much less likely for a radical to bump into a radical. Eventually, however, that happens. So we also have what's called termination steps. With termination steps, we go from 2 radicals to 0. It could happen that a chlorine radical bumps into a chlorine radical, giving a new molecule of chlorine. It could happen that a chlorine radical bumps into a methyl radical, giving another molecule of chloromethane. Or it could happen that a methyl radical bumps into a methyl radical, giving a molecule of ethane. So there are several different termination steps are possible, but these propagation steps are going to happen millions and millions of times before the termination steps start to happen. So it's important to keep in mind the initiation step, the propagation steps that undergo chain reaction, and then finally the possible termination steps. Next, let's consider both the reactivity and selectivity of chlorine versus bromine. If we have 2-methylbutane and we carry out a radical halogenation with chlorine or with bromine, let's think about the possibilities. We can generate a radical here or here. Those are the same as each other, but it's a different radical here, a different radical here, and a different radical here. So this gives us 4 possible products. So we can get some of this, we can get some of this, we can get some of this, and we can get some of this. Notice also that we have converted this into a chirality center, so we're actually going to make this product as a mixture of enantiomers. And here we generated a chirality center, so this one will also be made as a mixture of enantiomers. So we kind of get quite a mess. Chlorine is highly reactive, but not very selective. So keep in mind, this product is formed via a primary radical. The second product is formed via a tertiary radical. The third one is formed through a secondary radical, and the fourth one is formed through a primary radical. Now, tertiary radicals are more stable than secondary, are more stable than primary. So in terms of rate of reaction, it's going to be faster to be able to make a tertiary radical than it is to make a secondary than it is to make a primary. But we also have to keep in mind the number of hydrogens that are present. There's only one hydrogen that can be abstracted to form this tertiary radical, whereas there are 6 hydrogens that could be abstracted to form the primary radical that leads to this product. So it is possible to look at information on the relative reactivity of primary versus secondary versus tertiary hydrogens and multiply that by the number of those hydrogens in order to figure out the ratios of products. So it turns out we are going to make 29% of this product, 24% of this one, 33% of this one, and 14% of this one. Now, when it comes to bromine, bromine is less reactive, but it is more selective. So we can form the same possible compounds. So we can get this, and we can get this, and we can make this, and we can make this. Once again, this will be a mixture of enantiomers, and this will be a mixture of enantiomers. But what we get here is 0.33% compared to 90%, compared to 9%, compared to 0.17%. So with chlorine, the relative reactivity of primary compared to secondary compared to tertiary is 1 to 3.5 to 5. You don't have to know these numbers. I just want to go through an example. So although this is less reactive, the other positions are 3.5 or 5 times as reactive. The fact that we have multiple hydrogens, that then increases the likelihood of reaction through a primary radical. But for bromine, the relative reactivity of primary versus secondary versus tertiary is 1 to 82 to 1640. So there is a huge difference in reactivity. And reaction that occurs through a tertiary radical is much, much, much more likely to happen. So when it comes to predicting the products of a radical reaction with chlorine, I want you to recognize that all of these products are going to form. I'm not going to ask you to calculate the percentage, but I want you to know that you are going to get a significant amount of all of the possible products. When it comes to reaction with bromine, because bromine is so selective for reaction at the tertiary position, which occurs through a tertiary radical, we get the product from the tertiary radical as by far the major product. So if I asked you to predict the products of this reaction, I expect you to draw all 4 of these products and to specify that you get these as a mixture of enantiomers. If I asked you to predict the products for this one, I would expect you to say this as your major product. And it's not necessary to draw the others because they are minor in comparison. So to summarize what we get with radical halogenation, are these halogenation reactions actually useful? Well, with bromination, this is only useful when the starting material has tertiary hydrogens to give a tertiary radical. So in this case, if a hydrogen atom is abstracted from here or here, we get a primary radical. Here or here, we get a secondary radical. So this is going to be very, very slow. So not a very useful reaction. Here, we could either abstract a hydrogen from these to give primary radicals. That's not going to happen. Or we could abstract a hydrogen from here, which will give, as an intermediate, a tertiary radical, which then reacts to form this bromide almost exclusively. So when the starting material has tertiary hydrogens, that can give a tertiary radical that leads to a tertiary alkyl halide. This is a very useful reaction. For chlorination, this is going to be useful only when the starting material has equivalent hydrogens. So here, the reaction could occur at these positions to give the same product, or at these positions to give the same product as each other, but different here. And so this isn't going to be very useful because even if we get monochlorination, we're still going to get a mixture of products. This reactant worked well for bromine, but because chlorine is highly reactive and not very selective, we're still going to get a mixture of products. So still not very useful. But when we have something like cyclohexane, all of these positions are equivalent. And so if monochlorination occurs, we are going to get this product, and that's it. So this would be a very useful reaction. So there are limitations to radical halogenation reactions, but as long as we take into consideration the different mechanistic details, we can carry out these reactions effectively and selectively.